Alright, next we will get some formulas for finding an antiderivative. We have some really nice formulas for finding derivatives, and we should be able to use those formulas to find corresponding formulas for finding antiderivatives. So we'll start again with our table of a function and its derivative, and we'll try to construct a corresponding table. Now you notice I have two labels here. We can think about this corresponding table as I give you the derivative of a function and you give me what the original function is. Or another way to think about the columns of this table is if I give you a function, you tell me what the antiderivative of the function is. So two different ways of looking at these two columns of the table. Either way, this is going to be the derivative and this is going to be the original function. So we start out with a couple of the examples we had from last time. If x is the function, 1 is the derivative, if x squared is the function, 2x is the derivative, if x cubed is the function, 3x squared is the derivative, and in fact the power rule says if we have x to the n being the function, then the derivative is n times x to the n minus 1. We pull the exponent down and we subtract 1 from the exponent. So can we make an antiderivative formula out of this? Well, let's see. When we took the derivative, we took the exponent down, and the new exponent is 1 less than the old exponent. So if we start out with a function with an exponent of n, that's the derivative, then the antiderivative, or the original function, has to have an exponent that's 1 more than the derivative's exponent. So we should have x to the n plus 1. And here we multiplied by the exponent. So here we're going to do the opposite. We're going to divide by the exponent. So let's just check this rule. Remember, we can check a rule for antiderivatives by saying, well, this row in this table means that if this is the derivative, this is the original function. In other words, if I take the derivative of this, I should get x to the n. And remember, for the general form, I can always add a constant and won't change the derivative being x to the n. So let's check this rule here. What I'm going to do is take the derivative of this, and I should end up with x to the n. So the derivative of, let's do it up here, the derivative of x to the n plus 1 over n plus 1. What do? I take the exponent down, so this is equal to n plus 1 times x to the n plus 1, and then I subtract 1 when I take the derivative. So that's just going to be x to the n, and then I have this divided by n plus 1 right here, and the divided by n plus 1 cancels with the n plus 1 right there, and so I just get x to the n. And adding that constant on just adds a plus 0 for the derivative, so I still get x to the n as the derivative. So I've just verified that the derivative of this function is indeed x to the n. So now we have a general formula for the antiderivative of something that looks like x to the n. So for example, x to the 100, the antiderivative of x to the 100, I increment the power by 1, so I add 1 to the power, x to the 101, and then divide by that new power, the n plus 1. And then I can always add a constant, so I make sure to indicate that by putting plus c, and I have the antiderivative of x to the 100. So we could do a lot more derivatives than just using the power rule. We had many more derivative rules. So let's continue our table. I'll continue the table down here. So if we have f of x, f prime of x, let's see, if we had original function of sine of x, then the derivative was cosine of x. If we had the original function of cosine of x, then the derivative is negative sine of x. And let's keep going for a little bit. We got tangent of x. The derivative of tangent of x is secant squared x. The derivative of cosecant x is negative cosecant x with tangent cotangent x. The derivative of cotangent x is negative cosecant squared x, and the derivative of secant x is secant x tangent x. And then we had a few derivatives involving exponents and logarithms that we need to make sure we get down. The derivative of e to the x was just e to the x. The derivative of natural log of x was 1 over x. And this held if x was not equal to 0. And in fact, we could be a little bit more precise. Remember, natural log can't have any negative x's as well, and we took care of that in class by saying, well, if we take the derivative of natural log of the absolute value of x, then we still got a derivative of 1 over x. But again, x couldn't be equal to 0. And this covers almost all that we have, except we had a to the x. The derivative of a to the x was a to the x natural log of a, and the derivative of log base a of x was 1 over natural log of a times x. So now let's make the corresponding antiderivative table. I'm going to use these labels here with f of x and the integral sign just to make sure that we see this notation a little bit. So if I have a function, question is, what is its antiderivative? Sometimes we call this notation the indefinite integral. The other day in class we saw what we call the definite integral. When we don't have numbers here, it means just take the antiderivative, or sometimes we say this is the indefinite integral of f of x. So we can just basically read off our table. Here's the derivatives, here's the original functions. We'll make a few changes as we go along. If the derivative of the function is cosine of x, the antiderivative is sine of x. So we get this from this rule right here. But we could also add any constant, so the general form for the antiderivative is sine of x plus c. So that means sine of x plus some constant. The derivative of sine of x plus some constant is cosine x. Instead of writing negative sine x, I'm going to write sine x here. So if our derivative is sine of x, what's the original function? Well, the original function is negative cosine x plus some number. And so what did I do? We can check this by taking the derivative of negative cosine x plus c. So let's do that over here. The derivative of negative cosine x plus c is, well, let's see, the derivative of cosine x is negative sine x, but then we have a negative there, so we get sine x. And then plus c, the derivative of c, a constant, is just 0, so we got sine of x. So this verifies that the antiderivative of sine of x is negative cosine x plus c. And we can almost copy some of these formulas over. Secant squared x, if the derivative is secant squared x, then the original function looked like tangent x plus a constant. If the derivative was cosecant x cotangent x, then the original function looked like negative cosecant x. And again, I did the same thing as I did here for this row, sine x to negative cosine x plus c. If you take the derivative of negative cosecant x, then you get negative of this, which is just cosecant x times cotangent x. And if the derivative was secant x tangent x, then the original function must have been something that looks like secant x don't ever forget that plus c, because really, if you don't put the plus c there, then that's effectively saying that the c is equal to 0, that you're just adding the 0 constant. But in reality, your original function might have been some other constant. Your original function might have been negative cosecant x plus 1. If you forget the plus c, then you might not end up with what the original function was. And e to the x, this is probably the easiest one. If the derivative is e to the x, then the original function must have been e to the x plus some constant. If the derivative is 1 over x, if x is not 0, then the original function must have been something like the absolute log of the absolute value, natural log of absolute value of x. If the derivative is, and here I'm going to do something a little simpler than what's in our table here, if the derivative is a to the x, this means a is just a number, so like 3 to the x or 4 to the x. Well, here, when I took the derivative, I multiplied by natural log of a. So when I take the antiderivative, I'm going to do the opposite of that. I'm going to take a to the x and divide by the natural log of a. And let's just double check this. The derivative of this function should be this. So let me add my plus c's here. So the derivative of a to the x over natural log of a, let's just do it out here to the side. The derivative of a to the x over natural log of a, add my constant, is equal to, well, the derivative of a to the x is a to the x natural log of a, and then I take the derivative of my constant and I get 0, and notice that the natural logs cancel out, so I just get a to the x. So the derivative of this function right here is a to the x. That means the antiderivative of a to the x is this function right here. And one more rule. What if I have something that looks like 1 over the natural log of a times x? Well, the derivative, the antiderivative is log base a of x. There's a big table in section 5.1 that has all these antiderivatives. You can go look at those and check some of your understanding of these antiderivatives.